Hello, ma'am. Hello, ma'am.
Good evening, sir.
Yes, ma'am. Start பண்ணலாமா? Can I start, ma'am?
Just a second.
Yeah, ma'am.
You can start now.
Good evening, sir.
Yeah, ma'am. Good evening, Ajay. Ajay is there. Okay. Yesterday, did you understand, Ajay, what I was talking?
Yes, sir.
Very sure. Should we continue with that, or
Yes,
do I?
sir. Yes, sir. Understood, sir.
Understood. Okay. So, a few more compounds we shall do. Yesterday, we learned it for an octahedral complex. We learned for a tetrahedral and a square planar complex, and then we'll continue possibly. All right. So, valence bond theory is right so far. Yeah.
Yes, sir.
Yeah. Now the next molecule is explain the structure of NiCN4 2 minus based on valence VBT. Nickel tetracarbonyl. The name of this is IUPAC name for this is tetracyanidonickellate. Because it's an anionic complex, therefore it is nickelate, and oxidation number is 2 ion. Tetracyanidonickellate 2 ion. This is the IUPAC name of this complex. We'll have to learn the structure of this complex. We'll try to understand the structure possibly. The first point is the central metal atom here in this complex is nickel. Atomic number of nickel is what? Atomic number of nickel is 28. What is the atomic oxidation state of nickel? As a whole, the charge is 0. As a whole, the charge is -2. As a whole, the charge is -2. Cyanide is a -1, negative ligand. -1 into 4 is -4. And nickel, we don't know. We take it as X. So X will be equal to +2. So oxidation state of nickel is, oxidation number of nickel is +2. What is the ground state electronic configuration of nickel? What is the ground state electronic configuration? Ground state electronic configuration. It's argon configuration. Argon is 18, 4s2 and 3d8. This is the electronic configuration of nickel in what state? Ground state. But since nickel has +2 oxidation state, what will happen is outer 2 electrons will be removed. What's the outer 2 electron? 4s2. These electrons will be removed. When these electrons will be removed, what will be the electronic state of nickel in excited state? Excited state electronic configuration. Excited state electronic configuration is argon configuration and 3d8. So far, did you follow?
Yes, sir.
Now, what is the coordination number of nickel? What is the coordination number of nickel? How many monodentate ligands it has? How many monodentate ligand it has? It has 4. Therefore, coordination number of nickel is how much? 4. Yes or no?
Yes, sir.
Yeah. Now, the first point in the valence bond theory, the postulate is the central metal has to create definite number of vacant orbital. In order to understand that, we will write the electronic configuration of nickel in excited state. In excited state. In the excited state, the electronic configuration of nickel will be, we'll write the outermost orbit. D subshell, it has 5 orbitals. The names we will learn later. This is 3D. Already the 4s atomic orbital was there. It is 4s. Right. The next higher orbital possible is 4p. Next higher orbital possible is 4p. Now, if you observe the electronic configuration, nickel, it is 8 electrons. So 1, 2, 3, 4, 5, 6, 7, and 8. It has 8 electrons. Now, cyanide is a ligand here. Cyanide is a strong field ligand or weak field ligand. Cyanide is a strong ligand or weak ligand. Cyanide is a strong ligand. When,
Strong, sir.
yeah, strong ligand. When cyanide is approaching a strong ligand, when it approaches the central metal atom or ion, that is nickel, what should take place? Pairing of electron within the metal takes place. Pairing of electron within the metal takes place. When we say pairing of electron within the metal takes place, what happens is this electron gets paired with this. When this electron gets paired with this, what happens? This becomes empty. This becomes vacant. Are you able to understand what I'm telling? So, metal takes place, creating 1d orbital, 1 s orbital, and 2 4p orbital vacant. Now, these vacant orbitals hybridize, undergoes hybridization. When we say this hybrid orbital undergo hybridization, see what happens. When they get paired up, what happens? You see, d subshell, we will write like this. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8. This becomes empty. And next 4s is empty already. And 4p, we need 2. So this is 4p. Because the coordination number is 4, the central metal has to create only 4 vacant orbitals. Now these 4 vacant orbitals, they have to undergo hybridization. When I say they have to undergo hybridization, they undergo hybridization to form 4 dsp2 hybrid orbitals. So how many hybrid orbitals are formed now? It is 4. What's the name of the hybrid orbital? It is dsp2. Now, when I say dsp2, I can write the dsp2 orbital like this. 4 orbitals are there. We can write the 4th orbital like this. This is nothing but dsp2, 4 orbital. Now I can write a statement saying 4 cyanide ions donate 4 pairs of electrons to 4 dsp2 hybrid orbitals. So if they donate, what happens? Now ligands, there are 4 ligands, cyanide ion 4. So that we represented by X. These are the electrons donated by the ligands. So what type of bonding is formed between the metal and the ligand? Coordinate bond is formed. Therefore, what will be the structure of this? The structure of this is nickel at the center, square planar. So 4 corners of a square, you will have cyanide ion, Cn, 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 Cn. And the charge is 2 minus. Now, what is the magnetic property of this? See, nowhere we have unpaired electrons. Since nowhere we have unpaired electrons, it will be diamagnetic. And what will be the structure? It will be square planar. Did you follow this?
Yes, sir.
Did you follow? Go through this quickly. One more we are going to learn, and then we'll go to the next part of the topic. Go through this quickly. Nickel atomic number is 28. Oxidation of nickel is +2. Therefore, the excited state electronic configuration of nickel will be argon configuration 3d8. Since the coordination number of nickel is 4, it means the central metal atom or nickel has to generate or create 4 vacant orbitals. How these 4 vacant orbitals are created. Now, this is the electronic configuration of nickel in the excited state. But when cyanide ion, it's a strong ligand, remember, strong ligand. When cyanide ion approaches the central metal, what happens? Pairing takes place. And this d orbital becomes what? Empty. That is what here we have shown. And already 4s is there, which is vacant. And also we have what? 4p, which is also vacant. Now what happens is creating one d orbital, one s orbital, and two p orbitals. See, this is 2p orbital, 1s and 3. These 4 orbitals undergoes hybridization to form 4dsp2 hybrid orbital. Now, more precisely, if I have to write, I will write like this: nickel, it has 4 hybrid orbitals. These are the 4 hybrid orbitals now. 4 hybrid orbitals. Now, ligand, cyanide ion. If I write cyanide ion here, this cyanide ion donates a pair of electrons to the central metal atom. Therefore, coordinate bond is formed. So we have to represent the structure like this. So here also maybe a cyanide ion like this. Otherwise, we can represent it in this way. This is simple. The arrow mark clearly indicates cyanide donates a pair of electrons to nickel. Therefore, a bonding is formed between nickel and cyanide. Followed?
Yes, sir.
Yes, sir.
The next example we will see, that is Cn, Cl4 2 minus. Cl4. It is not Cen, it is Cl. Cl. Chlorine. Tell me what can happen. Is chlorine a strong ligand or a weak ligand? The explanation
Sir, it's a strong ligand.
here. Chlorine is a weak field ligand. Chlorine is a weak ligand. When chlorine is a weak ligand, will pairing take place? Pairing will not take place.
No, sir, it won't.
When so chlorine ion approaches, it's a weak field ligand. Therefore, no pairing takes place. This will remain as such. Now what happens? Still the coordination number is 4. We need 4 orbitals. Therefore, creating d orbital will not be there. Creating one s orbital and 3p orbital. It is not 2, it is 3 here. Creating one s orbital and 3 4p orbital. So the vacant orbital undergoes hybridization. The vacant orbital undergoes hybridization means what? How do I represent that? I can represent like this here. How do I represent? I can represent this. This is d orbital. This is d orbital. This will remain as such. 1, 2, 3, 4, 5, 6, 7, and 8. Now 4s is 1, and then we have 4p. 3. These orbital, this vacant orbital, that's 4s and 4p. They undergo hybridization to form 4 sp3 hybrid orbital. What will be the name of the hybrid orbital formed? It will be sp3 here. Now this 4 sp3 hybrid orbital will accept 4 pairs of electron from Cl minus. All right. So the hybrid orbital hybridization is sp3. So what will be the structure? Whenever a molecule undergoes sp3 hybridization, what is the shape of the molecule? The shape of the molecule is tetrahedral. The shape of the molecule is tetrahedral. How do I represent a tetrahedral molecule? Nickel at the center, one chlorine, another chlorine, another chlorine here, and another chlorine out. So the charge is 2 minus and 2 minus. What's this? The molecule is paramagnetic. Why paramagnetic? You can see unpaired electrons are there. Therefore, this molecule will be what? Paramagnetic. Did you follow?
Yes, sir.
Ajay,
Yes,
did
sir.
you follow? Now, we have learned the valence bond theory. We will learn crystal field theory a little later today. Now, what are the limitations of valence bond theory? Before we understand the limitations of valence bond theory, we should understand something called as spectrochemical series. A 2-marker, what is spectrochemical series? This is arrangement of ligands in the increasing order of their strength is called as Spectrochemical series. What is spectrochemical series? Arrangement of ligand in the increasing order of their strength. That means halogens are weak. The halogens will be on the left side. And you can see these all are strong. They will be on the right side. So from the least to the stronger. So arrangement of ligands according to the increasing order of their field strength is called as the spectrochemical series. Now, what are the limitations of valence bond theory? Now, we spoke about valence bond theory. I talked about few of the molecules now. Now, when we spoke about few of the molecules, yesterday we spoke about two molecules, cobalt complex. We spoke about nickel complex here. Did we speak about the color of the complex? Did I tell anything regarding the color of the complex?
No, sir.
No. So that means
No,
valence
sir.
bond theory fails to explain the color of the complex. Did I tell what type of bonding is between the ligand and the nickel? Postulate does not tell the type of or the nature of bonding between the ligand and the central metal. That is the second demerit. Now, one is it failed to explain the absorption spectra. When I say absorption spectra, it is nothing but color. Why different complexes of same metal show different colors? That also failed to explain. So valence bond theory failed to explain the stability of the complexes. It failed to explain the stability of the complexes, and it also failed to explain what is high spin while other is low spin. Low spin, high spin, and it means what? Valence bond theory failed to explain. These are the limitations of valence bond theory. Now, what are the advantages of valence bond theory? Fairly successful in explaining the geometry, structure, magnetic behavior, whether it's paramagnetic or diamagnetic. So these are the two advantages of valence bond theory. All the other are what disadvantages of valence bond theory. Now you see, now these are the complexes. In your 12th standard, whatever complex is there, we mentioned, we learned. Now other complexes you should know in order to work out for competitive exams. See nickel 2+. See, these all are nickel complex. So far what we have is nickel complex. So nickel 2+, it is D8 system. That means we have 8 electrons in the d orbital. I have shown you writing, and 4s and 4p is the higher orbital. In case of nickel 2+, you can see 1 4s electron and 3 4p electron. They involve in hybridization to form sp3 hybrid orbital, 4 sp3 hybrid orbital. These 4 sp3 hybrid orbitals will accept 4 pairs of electrons. See, this dots indicates the electrons donated by the ligand. Therefore, the structure is tetrahedral. We learned just now, and it's paramagnetic. And this complex also I taught you now, NiCN4 2-. So it will be D2, DsP2. Just now I told, today we learned the structure. It is square planar and diamagnetic. And it's a general electronic configuration of nickel. And nickel tetracarbonyl and nickel hexaamine complex you should know. So in nickel tetracarbonyl, again the hybridization is sp3. Nickel tetracarbonyl is a neutral complex. It's a neutral complex. So the hybridization is sp3. And oxidation state of nickel here is 0 in nickel tetracarbonyl. And tetrahedral, it's diamagnetic. NiNH3 6 times 2+. Here the hybridization sp3d2. Oxidation of nickel is +3+2. It's sp3d2, outer complex, octahedral structure, and it is paramagnetic. Did you understand what's being written in the slide? Is it possible for you to find out the structure of different complexes when they give, other than what I taught you in the class? Can you at least try? Hello? Hello, are you there?
Sir. Yes, sir.
Yeah, please, please. All right. Likewise, you can see different manganese complex here. This is manganese complex and copper complex here. So all these are not there in the syllabus, but they can ask you for a competitive exam. Any complex they can ask you. They can ask you to predict the structure. They can ask you to predict the hybridization, or they can ask you to predict the magnetic property. So the slides you should go through. Since this valence bond theory has major demerits or limitations, to overcome that limitations, we have something called as ligand field theory. Now, this ligand field theory we don't learn. We will learn crystal field theory. Ligand field theory is not there in the syllabus. According to this theory, when the ligand comes closer to the metal atom or the ion, a field is created. This field tends to split the degenerate orbitals of the metal atom into different energy levels. The nature and number of ligands determine the extent of splitting. Energy gap between the splitted energy level determine the magnetic and spectral property, that is paramagnetic or diamagnetic, and color of the complexes. Now, what is this? I hope that you understood the statement. Now, we're going to learn crystal field theory in detail. This ligand field theory, ligand, when they approach the central metal atom, around the metal, a field is created. Now, the field which created tend to split the degenerate d orbital. What do you mean by degenerate orbitals? What do you mean by degenerate orbitals? What do you mean by
So,
tell me.
so I'm not sure, sir, but is it those d orbitals? Sir, the d orbitals in which the
What do you mean by degenerate orbital? Which the
So which will
splitting.
disappear? Which will disappear?
No
Sir,
disappear.
the electrons are not. Sir, the electrons do not circulate in those orbits, sir.
All right.
They exist.
All right. Degenerate orbitals means orbitals which have same energy is called as degenerate orbital. Now, for an example, if you take px, py, and pz, this is px, this is py, and pz. These are called as degenerate p orbitals. Now, coming to the d orbital, d subshell has 5 orbitals. Now, what are the names of that? dxy, dyz, dzx, dx square minus y square, and the last one is dz square. Now, all these 5 d orbitals will have same energy. Therefore, these 5 orbitals are called as degenerate d orbitals. What do you mean by degenerate orbitals? Orbitals which have same energy will be called as degenerate orbitals. Example, p orbital has 3 degenerate orbitals, px, py, and pz. Likewise, d orbitals has 5 degenerate orbitals. What are those? dxy, dyz, dzx, dx square minus y square, and dz square. You should know the names of the d orbitals. To learn crystal field theory, you should know. The first one is xy. After y, what we have? Z. So the second one is yz. After that, z, and come back to the first one, x, zx. And the fourth orbital is dx square minus y square, and the fifth orbital is dz square. All right. So whenever the ligand, see, this is metal. When the ligand approaches the metal, what happens? A field is created around the metal. This field which is created around the metal will make the d orbitals, split into different energy level. So this energy gap will predict the magnetic property as well as the spectral property of the complexes. That is called as what? Ligand field theory. That's called as what? Ligand field theory. Did you understand? We're going to learn in detail. Did you follow what I'm talking about?
Yes, sir.
Now, coming to an important concept, that's called as crystal field theory. This theory was proposed by Bethe and Van Vel Orgel in 1952. Applied this theory to coordination compounds. And in this theory, ligands are treated as point charges. In case of anion, and dipoles in case of neutral molecule. So ligands, according to crystal field theory, all right, ligands are treated as point charges in case of anions and dipoles in case of neutral molecule. And dipole in case of neutral molecule. Now, 5 d orbitals are classified as, you can see here, 3 d orbital xy, yz, and zx are oriented between the coordinates, and they are called as T2g orbital, and the 2 d orbital, that is dx square minus y square and dz square, oriented along the xy axis, and they are called as what? EG orbital. Don't get confused all this. Due to the approach of ligands, the 5 degenerate orbital splits. Splitting of d orbitals depends on the nature of the crystal field. The energy difference between T2g and EG level is designated by delta, and it is called as crystal field splitting. Anyways, don't worry about it. I'm going to teach you now in detail the postulates of crystal field theory. Now, this crystal field theory, majorly, it has only 2 postulates. What are the 2 postulates of crystal field theory we're going to learn now? And then we're going to learn some of the complexes, structures based on crystal field theory. While going outside, students, hello? Are you
Yes,
hearing?
sir.
Yes,
While
sir.
going to school, college, all right, keep cotton in your ears and go. The weather is very bad, all right, easily infected. Keep cotton in your ears and go, all right?
Yes,
So
sir.
major
Yes,
sickness
sir.
no, be avoided. Don't forget to do that. I missed it for 2 days and I'm suffering with overconfidence. Even in summer, I used to keep cotton, and this cold weather somehow I missed. All right. Now coming to crystal field theory. Now, what are the postulates of crystal field theory? Postulates. Now, I hope you understood what is degenerate orbital. What is degenerate orbital? Orbitals in which the energy of them is same is called as what? An degenerate orbital. Degenerate orbitals ಅಂತ ಹೇಳಿದ್ರೆ it means orbitals which are same energy. It's called as degenerate orbital. What's the postulates of crystal field theory? CFT stands for crystal field theory. There are majorly two postulates. The first one is crystal field theory clearly says the bonding between metal and ligand is purely electrostatic. Purely electrostatic. When I say purely electrostatic, it means the bonding is ionic. Because if you remember one of the postulates what we were learning today in crystal field theory, the ligands are considered to be a point charge in case of anionic ligand, and in case of a neutral molecule, it is called as a dipole. All right. So when I say anion is negative and metal is positive, the bonding between the metal and the ligand should be what? Ionic. Or if the bonding between the metal is positive, and if you say neutral molecule will have polar molecule. Again, positive, negative character will be there. I'll give you an explanation. So again, there will be force of attraction between these two. Therefore, we say the bonding, or the crystal field theory postulate, first postulate is the bonding between the metal and the ligand is purely electrostatic or purely ionic. The second point is the attraction between the metal and the anionic ligand. See this? The attraction between the metal and anionic, negatively charged. Anionic is negatively charged. Anionic ligand is what type of interaction? Ion-ion interaction. What type of interaction? Ion-ion interaction. Now, for an example, if you take metal is electropositive. If you take a ligand like Cn minus, it's a negatively charged. This interaction will be what now? This is an ion and this is also an ion. Therefore, it is called as ion-ion interaction. Now, similarly, if we take attraction between metal and neutral molecule, it is ion dipole interaction. I'll explain. Ion dipole interaction. What is this ion dipole interaction? Now, metal is positive. Metal is positive. Now, if you take water, H2O, I'll write O, H, and H. Now, water is electropositive, hydrogen is electropositive, and oxygen is electronegative. So this is the representation. Now, this oxygen and metal will have interaction. Therefore, it's called as, this is an ion, metal is an ion. This is a molecule. It's a dipole molecule, dipolar molecule. So therefore, the interaction between this will be metal and what? Dipole interaction. Did you follow these 2 points?
Yes, sir.
Very important. These two are the major points in case of what the crystal field theory. The third postulate in the crystal field theory is third and fourth. The central metal atom is situated in the electric field called ligand, and this is called as crystal field. Don't worry about this point also. Now the next point is when the ligand approaches the central metal, when the ligand approaches the central metal atom or ion, the ligand approaches the central metal atom or ion, the degeneracy, that means the degeneracy is lifted. The degeneracy is lifted, meaning the d orbitals undergoes splitting. And this is called as crystal field splitting. This is called as crystal field splitting. What did I tell? When the ligands approach the central metal, the degenerate orbital, the degeneracy is what? Removed. The degeneracy is removed means what happened? The d orbitals undergoes what? Crystal field splitting. Did you follow?
Yes, sir.
Yes, sir.
Yeah. Just give me a second. All right. So degeneracy is lifted. So this d orbital will undergo splitting. When we say d orbital will undergo splitting, that splitting, the difference between the two d orbitals energy will be called as crystal field splitting energy. Now, just I want you to go through this postulate again, three postulate, because I have to pictorially represent. The bonding between the metal and the ligand is purely electrostatic. That means ionic. Metal and the ligands are attracted through an ionic bond. The second point is two types of attraction happens between the metal and the ligand. What are the two types of attraction? The first one is the attraction between the metal and the negatively charged ligand, anionic ligand, is through ion-ion interaction. Next one, the attraction between the metal and the neutral molecule is ion dipole interaction. I clearly explained what is dipole. Similarly, if you take ammonia also, NH3. So hydrogen is positive, nitrogen is negative. So interaction will be towards what? Metal and what? The negatively charged. All right. Now, when the ligand approaches the central metal atom or ion, the degeneracy is lifted and the d orbital undergoes splitting. And that's called as crystal field splitting. These are the 3 points in crystal field theory. Postulates. They can ask you postulates of crystal field theory. Now, we're going to explain some of the structures of the molecule. I want you to pay attention. All right. Now, crystal field theory explains the magnetic property, spectral property, all that detail. Now, we will try to understand. It is different from valence bond theory. It is not same as valence bond theory. Now, first we will learn the general representation, and then we will go for the other. Specific we will learn. Are you following, students?
Yes, sir.
Yeah.
Yes, sir.
Now, see, how do you understand this crystal field splitting? Now, this is based on energy. This is based on energy. Now, I have a metal ion, isolated metal ion in gaseous state. This is isolated metal ion in gaseous state. Now, this isolated metal ion will have 5 d orbitals like this. And they are called as degenerate orbitals. They're called as what orbitals? Degenerate orbitals. This is nothing but dxy, dyz, dzx, dx square minus y square, and dz square. This is nothing but what orbital? Now, degenerate orbitals. When ligands approach them, what happens is this around the metal, a field will be generated. When around the metal field will be generated, it means the metal will gain more energy and go to a higher state like this. Still, you can see it is degenerate orbital only. Now, this will be called as what? And this is in the ligand field. In the ligand field. The ligand field. See, degenerate C is still maintained. No splitting. Splitting is not taking place. But when the ligand comes very close to it, what happens? Due to repulsion, this d orbital gets split like this. They get split like this. When we get split like this, 3 orbitals will go to a lower energy level called as T2G. G stands for Jarade. T and 2 is a representation. And totally 5 orbitals are there. 3 goes here, the other 2 goes here. And this is called as EG level. EG is called as Un Jarade, or we represent it as only what EG. Don't worry about the names of it. This is French name. All right. This is for octahedral complex. This is for octahedral complexes. This kind of splitting happens for octahedral complex. So dxy, dyz, dzx. And this will be dx square minus y square and dz square. This difference in energy between the 2 orbital is called as crystal field splitting energy, represented by delta. So this energy is represented by what? Delta. No problem with this? No problem?
Yes, sir. No problem.
All right. Now I have to explain the crystal field splitting in octahedral series, octahedral complex, and I also have to explain in what? A square planar complex. Now, in case of square planar complex or tetrahedral complex, not square planar syllabus, you do not have square planar, you have only tetrahedral complex. What happens is this becomes reverse. When I say this becomes reverse, what happens? These 3 orbitals will go on top. When I say these 3 orbitals will go on top, what will be this electronic configurations you will have? This is represented as E, dxy, dyz, dzx. In case of tetrahedral complex. And here you will have only 2 orbitals. You will have only 2 orbitals. What is the name of those 2 orbitals? The name of those 2 orbitals will be dx square minus y square and dz square. This is represented as only T2 level. Lower energy level is represented as what? Only T2. It is not G. For octahedral, we represent it as G. All right. So in tetrahedral complexes, we do not represent. The configuration only shifts, splitting. All right. 3 orbitals goes on the top and 2 orbitals comes down. This is in case of what? Tetrahedral splitting. Did you understand? The reverse of this is what? Octahedral. And this is nothing but tetrahedral. Did you follow?
Yes, sir.
Oh my God.
Follow, sir.
Yeah. Now, Ajay, did you follow?
Yes, sir. Follow,
Yeah,
sir.
yeah. Now, we'll learn this crystal field splitting now in detail. So I'll try to erase it and try to write possibly neat. Let's see. If you have understood this, then it becomes very easy for us to talk about the octahedral complex and tetrahedral complex quickly. So we're going to learn now crystal field splitting in octahedral complex. Crystal field splitting in octahedral complexes. Now you should visualize what I'm going to try. Now this is based on the energy. Now d orbitals, we have 5 d orbitals. In the isolated gaseous atom, we have 5 d orbitals. Degenerate d orbitals. It is an isolated gaseous atom. This is an isolated gaseous atom. So what do you mean by degenerate orbitals? Orbitals having same energy will be called as degenerate orbitals. Now, when the ligand approaches these degenerate orbitals, what happens is the energy, there will be a ligand field created. Therefore, what happens is the degenerate orbitals will gain more energy and gets elevated to higher level. Gets elevated to higher level. 3, 4, 5 gets elevated to higher level, but still degeneracy is maintained. Now, when the ligand comes close to it, what happens is, when the ligand comes close to it, what happens is, this ligands undergo splitting. Ligands undergo splitting. Now, in T2G, 2 level, and at the lower energy, we have 3. The lower energy orbitals are called as T2G, and higher orbitals are called as EG. Higher orbitals are called as EG. The center dotted line, what I've written, is called as barycenter. Is called as barycenter. What is this barycenter? The increase in EG level and decrease in T2G level should be balanced. Increase in EG level and decrease in T2G level, the energy should be what? Balanced. Now, what is the energy associated with one T2G orbital? Totally, how many orbitals we have? 5. Out of 5, 2 is in which one? EG. So this is represented as the energy of delta naught. Delta stands for energy and naught indicates octahedral complex. So this will be the energy of what? Each T2G orbital. 2 divided by 0.5 is how much? 0.4 dq. This delta naught you can represent, or you can represent as dq. Now, totally we have 5 orbitals. Out of the 5, 3 are in T2G. Therefore, I write 3. Here you get a delta naught, or it is this is plus 0.6 dq. And this is minus 0.4 dq. Why it is minus 0.4? There's a decrease in energy. Therefore, it is what? Minus 0.4. Minus 0.4 into 3. Minus 0.4 into 3 is how much? Minus 1.2. Plus 0.6 into 2. It's again how much? Plus 1.2. Plus 1.2 and minus 1.2. So the energy gets what? Cancelled. Therefore, the complex remains what? Stable. Now you should tell me why there is a decrease in energy, T2G. What are these orbitals? dxy, dyz, dzx. And this is, you should mention dx square minus y square, and this is dz square. Why there is an energy increase for these 2 orbitals and why energy decrease for these 2 orbitals? The decrease in energy or increase in energy can be explained like this. Oh, here it is mentioned here, octahedral crystal. Okay, it's all the same. I'm also explaining the same thing. I want to write and explain. So now, if you have an octahedron, so I'll write a metal like this. Octahedron, if I write like this is octahedral complex. This is octahedral complex. All right. Now this is a hybrid orbital, or else maybe we'll write like this. This is a hybrid orbital. This is a hybrid orbital of the metal. All right. Now, when the ligand is approaching, the ligand can approach the orbital of the metal directly. When the ligand approaches, the ligand orbital approaches the orbital of the metal directly, what happens? Metal also has an electron here. This also has an electron here. Therefore, more will be the repulsion. When more is the repulsion, what happens? Energy will be what? High. Therefore, what happens? In case of octahedral complex, what I was writing. See here, these 2 orbitals will get into a higher energy. That means ligand will approach directly on the axis of dx square minus y square and dz square. Therefore, energy will be what? More, and they go to a higher level. But if this ligand comes between the orbitals, metal orbitals, meaning if the ligand orbital is approaching in between the metal orbitals, what happens? There is no much of repulsion. Since there is no much of repulsion, what will happen is the energy will decrease. That is why there is a decrease in energy. That's a decrease in energy. So T2G level. So that means if I write dxy, what do you mean by dxy? If I write this is x orbital and this is y orbital, ligand will approach in between. Therefore, what happens? The repulsion will be minimum. Therefore, there will be a decrease in energy. Did you follow this, students?
Yes, sir.
Yes,
Now,
sir.
I gave you the energy concepts also. All right. So what is this -2? What's that? 2/5 and 3/5. All this I gave you. Now the reverse of this will be for tetrahedral splitting. What is the reverse of this tetrahedral splitting? I'll try to use this and explain. See here. See here. Instead of writing box, they have mentioned what lines? 5 orbitals here. Metal d orbitals, and when the ligands approach, they gain energy. Electric field is created, and they get elevated. All these are degenerate. But when the electrons approach much closer, what happens? Splitting takes place. One is T2G level, the other one is EG level. XY, YZ, and XZ, 3 orbitals, and X square minus Y square and DZ square, 2 orbitals, 3/5 and 2/5. I explained this in detail. Now coming to the tetrahedral splitting, see this, it is the opposite. What is that opposite? DXY, YZ, and DZX. It means ligand approaches on the axis directly in phase. Therefore, what happens? The repulsion between the electrons will be what? More. Therefore, they gain what energy? More energy. In case of X square minus Y square and DZ square, the ligands come in between them. Splitting is what? Less. Therefore, they get what? Lesser energy. Actually speaking, it has to be mentioned as E and T2. It's not G. And you can see here delta T they have represented and delta T. Now, out of 5 orbitals, 3 goes to a higher level, therefore it's 3/5. 3/5 is how much? -0.6. And we have 2. -0.6 into 2 is -1.2. Now 2/5 is plus 0.4. Since we have 3 orbitals, plus 0.4 into 3, that is plus 1.2. So increase in energy and decrease in energy are balanced. Therefore, the barycenter is maintained. This is with respect to crystal field splitting in what complex? Tetrahedral complex. Did you follow these two? Did you follow?
Yes, sir.
Crystal
Yes,
field
sir.
splitting?
Yes, sir.
Yes. Now, coming to limitations of crystal field splitting. What are the limitations of crystal field splitting? What are the limitations of crystal field splitting? What are the limitations of crystal field splitting? First one is, this theory is applicable to metal ions with the d orbitals and does not explain about s and p orbitals. That's the demerit. So this is shown only for d orbitals. Splitting is only for d orbitals. We are not talking about s and p orbitals. This theory considers electrostatic attraction between the central metal and ligand. Hence, consider only ionic bonds between them, but does not account for covalent nature between them or coordinate bond. So crystal field theory does not account for the covalent nature between the metal and the ligand or the coordinate bonding between the metal and the ligand. Water is a stronger ligand than OH, which cannot be explained by the theory satisfactorily. These are the 3 the demerits of crystal field theory. All right, did you follow the students? Yeah.
Yes, sir.
Yes. Now, crystal field theory also explains the stability of the coordination compounds. What is the stability of the coordination compounds? Stronger the metal ligand bond, less is the dissociation in the solution, and hence greater the stability. When the metal and the ligand bonds are stronger, dissociation of those complexes in water will be what? Minimum or less. That means greater is the stability. Now, if you take cupra ammonium complex, CuNH3 4 times 2 plus, if you put in water, dissolve it in water, it dissociates to form copper 2 plus and 4 ammonium molecules. Since this equation is in equilibrium, you apply law of mass action twice. When you apply law of mass action twice, we get Ki. Whatever's on the right hand side on the numerator in square brackets, molar concentration, Cu2 plus into ammonia concentration. Since the coefficient of ammonia is 4, we write it to the power 4. We raise it to the power 4. And what is on the left hand side? The left hand side is this complex, CuNH3 2 plus. So stability constant of this complex is explained like this. So if we reverse it, reverse the reaction, CO2 plus 4 ammonia gives you the complex, and then you get K, right hand side on the numerator, whatever the left hand side of the denominator, that's called as 1 by K. Greater is the stability constant, stronger is the metal ligand bond. So K value is the larger, then the stronger will be the metal ligand bond. So this is with respect to stability of the coordination compounds. So crystal field theory explains the stability of the coordination compounds also. So what's the next part of the topic? Once you have learned with crystal field theory, I have to solve some of the questions based on crystal field theory and valence bond theory. We have not learned questions based on crystal field theory and valence bond theory. I think we should do it in the next class. All right, madam? Ma'am?